This is group 3 and it's our mechanical EDA. So we've got our bridge here and the force is applied at 2 points. So we made sure that we reinforced these spots here with the supports so that making sure that we move the force away from the bridge deck and into the supports as efficiently as possible.
Okay. We quickly identified that the lollipop sticks are much better under tension than compression. Under compression, the sticks buckle and swap and snap under a small load, whereas under tension, the lollipop sticks are almost unbreakable. The limiting factor when under tension becomes the glue joint rather than the stick itself.
Yeah. In terms of the bridge twisting, we concentrated on the length to width ratio, and we found out that using one stick was easy enough to build and efficient enough to withstand the load that we wanted. And we also added reinforcements to the bridge to make it more rigid and withstand a higher load.
So from our identification that the fact that the lollipop sticks were much better under tension, we decided to come together with a design that would mainly be under tension rather than under compression. So as you can see on our diagram here, we did a quick sort of primary stress regime schematic and sort of thought, right, how can we get most of the members in tension? And the best way to do that was to make a truss bridge which sort of hung underneath. The next sort of main concern was the fact that the bridge was under 2-point loading, so the actual areas of contact were an area of concern because of the fact that there'd be a very large pressure at that point. So we thought we'd load directly into the columns at those points rather than onto a member, so that it was less likely to buckle and snap along the top of the deck. And that then also allowed us to get the force very quickly into a tension member rather than in compression through the top of the deck, and then very quickly into the support. The next kind of concern was the fact that it was twisting, as just mentioned in the previous slide. And to do that, we made the bridge as wide as we possibly could while making it easy enough to build, and that meant keeping it one stick wide, and then also the fact that we added 3 trusses going into the screen rather than just 2 to give it an extra element of stability.
You're on.
Firstly, we realised that to complete the project we needed to consider time management, as it will be very important due to the time frame of 3 2-hour slots that we were given. Once we created basic targets for each session, we could focus on the specialisation of tasks. To do this, we set small groups to manufacture a couple of basic components, and another group to assemble another group to assemble these into trusses, and then another to assemble the trusses into a bridge. From the stress analysis of the structure, we identified which elements were in tension or compression. From this, we deduced members in tension should have the gluing surface of the joint maximised, and however, when a member is in compression, the structural rigidity should be focused on. This is done by increasing the ratio of cross-sectional area to length of the member, which will make it more rigid.
Okay, so as a result of the torsion caused by the test rig, we ended up with a lot of shear stress, obviously, which resulted in bending and thus a point failure due to stress concentrations in this corner here. Because tolerances are quite small, the design ends up being quite asymmetrical, and that's sort of why this happened, because the asymmetricalness of it led to that point failure in that corner, and the eventual twisting and causing it to fail. But before it reached that point, it did in fact take 1,550 newtons with a weight of 480 grams, so it ended up with a ratio of 3.23.